Okay, we're going to get into piecewise functions. Now, personally, not my favorite things. Chapter 1 is pretty much a review of last year, so just Chapter 1 is easing you into the course, but it's important to get all your fundamentals back. Let's look at a post office, okay? Because we're all familiar, possibly, with the post office. Let's say you're at the post office and they say, oh, well, if your letter weighs 0 to 100 grams, we charge you $1. And then they say, if it's 100 grams to 500 grams, we charge you $3. If it's 500 grams to 2 kilograms, that's a big range, but whatever, we charge you $8. And anything bigger than 2 kilograms, this never happens, by the way, but we would charge you 20. Now let's look at that. Now on the bottom, obviously up here on the y-axis is price, because we don't know what the price is, right? We don't know what the price is unless we know the weight, which makes the weight the independent variable. So everywhere here I'll go 0, and I'll do 100 here, and way over here I'll do 500, and 2 kilograms is the same as 2,000, so I'll put 2,000 here, way over here. Now let's have a look at that and see what prices we're dealing with. Well, whenever we're 0 to 100, they're going to charge us $3. So let's put some prices, or sorry, $1. Let's put some prices here. Let's put 20 here. We're going to put 8. We're going to put 3, and we're going to put 1. And we're just going to put it in here. Okay. So they won't charge us anything for 0. So 0 would have a circle in it. And that's an important thing to notice, that from this, it's actually when it's bigger than 0, because they're not going to make you pay for anything that doesn't exist. So it's bigger than 0. And all the way up to 100 grams, it's $1. So that means I would put a little circle here, because I'm not including the 0. And I'm going to, and it says up to 100 grams right there. And we'd have to figure out if I think it's included in that. So we put a solid circle there. I'm sorry, that's not a very good solid circle. But we would put a solid circle there. I'll do it like that. And that would mean that this one has to be bigger than 100 grams, because if you have something 100 grams here and 100 grams here, they don't know whether to charge you $1 or $3. So that means if we say the 100 grams up here is including that, we would actually just define this as when the object is bigger than 100. So we do when 100, oh geez, sorry. Let's do it with text. We do it like this. We'd say when 100 is smaller than x, but smaller or equal to 500. That's how we would do each of these range. 500 is smaller than x, is smaller or equal to 2 kilograms or 2,000 grams. And anything when x is bigger than 2,000 grams, it's the last condition, and we actually need the first condition in there as well. When 0 is smaller than x, is smaller or equal to 100. Now, here's the thing. If I said smaller equals, suddenly they're charging you $1 for something that weighs 0 grams, which is impossible. So we always have to say bigger, x is bigger than 0. And remember, whichever way the mouth of the sign is pointing to, that's the bigger side. So that means 0 is smaller than x, or x is bigger than 0. Up here, I can't have 100 is smaller and equal to x, because we have it right there. It's possible to make that next category include 100 by doing that, which means when you hit 100 grams, they're going to charge you the next level up. But right now, the way I'm doing it, I'm just going to do it like that. And the reason you can't have that is because then you no longer have a function. They don't know if to charge you $3 or $1 when it's 100 grams. So only one of the categories can have the 100 grams, and I've chosen the dollar. So that means from 100 to 500, including 500, which is what that equals means, it's $3. And that's why you have a smaller than here and not a smaller or an equal. Because again, if 500 was down here and up here, they wouldn't know to charge you $3 or $8. So you have to say not counting the 500, all the way up and including, that's what the equals is, 2,000. And that's why this is when x is bigger than 2,000 and not bigger or equal. So So that means that from 0 to 100 grams, they charge you $1. And you would include a solid circle here to say that includes the 100 grams, but this hollow circle say that does not include the 0. Then up here you have to put a hollow circle at 100 to say that we're now bigger than 100, all the way up, sorry, an empty circle, all the way up to a solid circle here to say including 500. And you join them with a line. And that essentially says if your package is anywhere from 100 to 500 grams, we're going to charge you $3. Not the 100 gram though, that's $1. And that is why it's solid down here saying we are going to charge you $1, and empty up here, which means bigger than 100, we're not going to charge you $3 if it's 100 up here. We're going to charge you the $1. That's what the solid means. And this solid here means if it's 500 grams, we're charging you $3, not the next level up. But you can see the next level up, $8 is 500 to 2 kilograms, which is 2,000. But not including 500, so we do a hollow circle all the way up to 2 kilograms, but it's including the 2 kilograms, so we do a full circle, and we join it with a line, which means anything from 500 to 2,000 grams is going to charge, post office is going to charge you $8. And then finally the last one is anything above 2,000 grams, so the hollow circle, and then we just have this line, and we would have this little arrow, which means everything bigger. That arrow just says it goes on forever. If it didn't go on forever, for instance, if the post office only dealt with a certain size package, they would end it at the size package they want it, let's say 4 kilograms, and anything bigger they'd say you have to arrange with someone else. Post office doesn't do that, but it'd be an interesting world if they did. So then you have an arrow saying the post office will handle anything bigger than that and charge you $20, which is ridiculous because then you could just ship your couch for $20. So they're always going to have limits all the way up. But this is just for example. How we would rewrite this? Well, we're calling the function, let's say, cost of postage. And notice that usually we do f of x, right? But eventually in this you're going to actually use the terms you're using. So I'll leave f of x then. But in this case we would do cost in dollars of postage in p, which means p is on our x-axis and c is on our y-axis. And that's how you always tell. This part will always be the y-axis and this part will always be the input or the x-axis. And then you'd have to have several ranges, and you would write it like this. And I'm just going to move our graph over a bit here. Just that. And you have several ranges, and they're pretty much the ranges I described or I wrote earlier. You would say the ranges are y can only be $3, sorry, $1, when 0 is smaller than x, smaller or equal to 100. It's going to be $3 when 100 is smaller than x and smaller or equal to 500. It's going to be $8, comma, when 500 is smaller than x, which is smaller or equal to 2,000. And it's going to be $20 when x is bigger than 2,000 grams. And you'd have the grams in there too. Okay. And what this says is depending on what x is, this is going to be your y. Depending on what x is, this is going to be your y. Depending on what x is, this is going to be your y. And this is called a piecewise function, I think it's called. And you put a bracket there to say that c of p is all of these conditions depending on what x is. And you'll notice there's a big gap, right? There's a big gap between here and here, so it's not like a flowing line like that. And this is called a discontinuous function because there's a big gap. Discontinuous. Okay? But you will find that you can have those empty circles and still have a continuous function. So we're going to get to that. But essentially discontinuous means I can't draw a line straight through all of this and fit on the graph. This is how it would look like, and this is a piecewise. Piecewise, do they call it? Pieces. Yeah, piecewise function. just means a function that uses different rules at different parts of x. And they're actually true to life. You won't use it a lot in so much. Well, you could use it in some science, actually. But you'd see it a lot in finance. You'd see it a lot on cost of businesses like profit, pricing. And it's surprisingly, business uses a lot of math to determine the best price they can get. They can price it at and make the best amount of money, sometimes to everybody's detriment when it comes to medicine. But anyway, this is the function there in piecewise. Sometimes you can have a function that says my f of x is going to be my f of x, and we're just going to get rid of price and all that. We're going to just use a normal graph. My f of x is a parabola, and I'm just going to say x squared. But I'm going to say it's only a parabola when x is smaller or equal to 2. And then after that, I'm going to say when x is bigger than 2, it's going to be the line. It's going to be a line. And then f of x is going to be equal to a line. So how that would look is I would have a line that goes through here to 0. And then when I reach x of 2, let's say this is x of 2 here, what would y be? It would be 4, right to there. And am I including the 2? Yes. So I would put a solid circle here, and I would put an arrow here to say this function goes on forever that way. But right here, my function changes into a line. When x is bigger than 2, we have a line. And actually, let's use 1, because that's going to be a more interesting case. So I'm going to just chop that down to here. And I'm going to say when x is smaller, or actually I'm going to say smaller than 1, it's a parabola. And when x is bigger or equal to 1, it's a line. Which means right here, when this ends, I actually put a hollow circle. And what's that coordinate? 1, 1 is the point that fits when 1 is x, y is 1. And then from that point on, I'm going to have a line, a straight line. We'll do it in red, which follows all the same rules of y is equal to x, which means at this here is going to be 2, 2. This here is going to be 3, 3, etc. And what about this one, the starting point? Well, it says bigger including 1, so that would get the red line would get the solid dot, and that coordinate would be 1, 1, which means my parabola ends at 1, 1, but doesn't include 1, 1, and my line starts at 1, 1 and includes 1, 1. Now, technically, this is a continuous line because I can draw a line right through that. And by the way, there's an arrow here to say forever after. And the reason I can draw a line through there is because when I reach 1, 1, it essentially hops onto the red line, but there was no discontinuity. It was a smooth transition. Every number below 1 is represented on the parabola, and every number including 1 above and above is represented on the line, which means that this is a piecewise, but it's also continuous. And this is important later on in calculus and rates of change, which means that if I was to write it, I would do f of x, and then I'd have it way over here when it's equal to x to the power of 2 when x is smaller than 1, but it's equal to just x, and I'll get that power of 2 in there, when x is bigger or equal to 1. And I'll get that power. And then I would also write a line bracket like this to say f of x is both of these functions depending on what x is. And that's how you would write it. Notice it's continuous. Now suppose, just suppose, I said x is bigger than 1 for the line and x is smaller than 1 for the parabola. In other words, they both have a hollow circle. They both have a hollow circle where 1, 1 is concerned. And if you want, I can do it in black as well to show that they both don't include it. And that means suddenly when x is 1, we have no value for y. It doesn't exist. Which suddenly that turns it from continuous to discontinuous, because that 1, 1 doesn't exist. It's not included in the in the, so it's if we got rid of this equal sign here, it's not included in the parabola and it's not included in the line, therefore it becomes discontinuous, and there's a big empty circle at 1 comma 1. Now Desmos can recognize this. You can do y is equal to x squared, there's my parabola, and then in rounded brackets you can say when x is smaller than 1, and there it is. Then you can do y is equal to x, and then in brackets you can say when x is bigger or equal to 1. And boom, suddenly we have the thing I just drew, and right there 1 1 is included, and we can slide anywhere. Oh, so on the red graph, see, on the red graph it says undefined, but on the blue graph 1 1 is defined. That's how you know it's continuous. Now watch what happens when I get rid of that equal sign. Now it's going to be discontinuous on the blue, undefined, and discontinuous undefined on the red, which means 1 1 doesn't exist and there's no continuity. This is discontinuous graph. So it's quite a bit different, and that's where you have to understand what happens when you put those equal sign in, because it generally affects your graph. And also in science, you usually want every dot represented. In other words, when it's discontinuous, it's no longer a useful function. I can't predict what happens when x is equal to 1 because y doesn't exist. Now, if that's the only exception, then yeah, and I can't think of a good example that exists in nature. Maybe the speed of light. You can't go faster than the speed of light, but who knows? Really, I'm not in any position to dictate what the exceptions are, but you can create exceptions. Might possibly exist in business. For instance, you can't create negative items or whatever. Anyway, my point is you need to spot when it's discontinuous and when it's continuous. Let's get to the problems. Sorry if I go on too long. You can always play at double speed. Graph each of these. So instead of graphing, I think I would prefer to use Desmos. And yeah, that's lazy. I'll go through how you would graph it. So you want to recognize the graph, and there's number 2 is part of this, so we'll keep it. You want to recognize the graphs and ask yourself what's happening before you get into how you're going to graph it. So I'm going to just put the graph thing here and the functions over here. All right, let's look. So it's saying when x is smaller than 1, it's just the number 2, so that's going to be a horizontal line. Y is 2. And then from up and including 1, f of x is going to be a line, 3x, so a slope of 3 on that line. So that means 1 is going to be included in both of them, but will it be continuous? Well, when x is 1 here, it's clear that's 2. When x is 1 here, what happens when we put it in through the formula? 3 times 1, we get 3. So what's going to happen is we're going to have a flat line, and then suddenly the line is going to start up here at 3, 1 comma 3. And there's going to be a big gap between it. But we can let Desmos do that. Let's make our first line equal to x, and then in brackets, when x is smaller than 1. So there's the first line. And then we can make our second line, y is equal to 3x, but when x is bigger or equal to 1. And boom, there's that big gap I was speaking of. Is this a continuous graph? Of course not. Notice that at 1, 1, it's undefined here. Oh, it's not y is equal to x over there. It's y is equal to 2. So there's the horizontal line. Notice at 1, it's undefined here, but at the blue line, it is defined because the 1 is included in the blue line. But there's still a big gap. So it's discontinuous. How would I make a connected line? Well, either make the second line 2x. Boom, suddenly I join that line. Or make the first line 3. And suddenly I can join where it starts there. So essentially you got to see where this one ends and this one begins to see if they're continuous. See, now look, in number 2, state whether it's continuous or not. That's why it's good to jump ahead in questions. Let's look at B. So this is a downward sloping line with a slope of -2 when x is smaller than 0. And when x is bigger or equal to 0, it's going to be x plus 4. So it's just going to be the line that's elevated by 4. Well, let's look at what this is when x is 0. When x is 0 over here, y is 0. When x is 0 over here, y is 4. Are they going to be connected? No, of course not. One ends at 0 and one starts at 4. But let's make sure. So we're going to put y is equal to -2x as our first line when x is smaller than 0. And when x is bigger or equal to 0, our new line is x plus 4. Boom, there's a huge gap. Sure enough, red line ends at 0, and it should not include 0. When x is smaller than 0. But it should not include 0. That should say undefined there. And when this starts, 0, 4 exists. That's interesting. That should say undefined at 0, 0. Let's follow it all the way down. Now, I wonder if it's, you know what I think it's doing there? It's counting origin. It's showing me where origin is as opposed, yeah, see, there's origins lighted up. Ah, so you got to slide it down the line to see that it's actually undefined. That 0, 0 it's showing me is actually the origin point on the graph, not the graph itself. So there's 0, 0. You see the hollow circle, it's undefined. And then at 4, 4, it's a solid circle. It's defined at 0, 4. However, it's not continuous. And it's very easy to see it's not continuous because when this line ends, y is going to be 0. And when this one ends, y is going to be 4. And how did I figure out that? By plugging the 0 into each of the formulas to figure out the y's. Let's look at this one. This is an absolute value, but only below when y is minus 2. So we're going to have something that at minus 2 is a normal absolute value, but stops right there and includes minus 2. And then anything bigger than minus 2, we're looking at a downward facing parabola. So it's going to be like that. And at minus 2, it's going to be right down there. And it's not going to include that minus 2. It's going to have a hollow circle because it says right there, bigger than. So are those connected? Are they going to be connected? Of course not. Let's let Desmos do the work for us, though. We're going to make the first one absolute value of x when x is smaller than minus 2. And we're going to see, oh, I got to put this in brackets, I think. There we go. And there it is. Okay. If I change that to like 7, you'll see more that it's an absolute value graph. It stops at minus 2. And then when x is bigger, not, oh, and it's supposed to be equal there, including the minus 2. And then when x is bigger than 2, we're dealing with the downward facing parabola, minus x, shift 6 squared. And when x is bigger than minus 2. Now, let's follow the blue line. It's undefined there. Down here, it's defined. So, technically, sorry, is this a function? Yes, it is, because it would pass the vertical line test. There's every value of y is represented, and there's only one unique x. Is it continuous? No, it's not. So all these were functions because they passed the vertical line test. When wouldn't it pass the vertical line test? If this one was smaller than minus 2 and this one was bigger than minus 2, that would mean at minus 2 it's undefined on both graphs, which means it's not a function because at minus 2 there is no y. It would not pass the vertical line test. But if one of them includes minus 2, it will pass the vertical line test, but it's no longer a continuous function. Okay, let's get to the next one. This one here is an absolute value graph that's been that's been shifted to the left by 2. That's because the 2 plus 2 is inside the absolute value. And only when x is smaller than 1. So it means at minus 2, I'd have a v, the vertex of the absolute value. And then it would start going up. And then from 1 onwards, but not including minus 1 rather, we're talking about a downward facing parabola that's been shifted upwards by 2. So let's see where this one ends. Where does this one end? Well, when x is minus 1, we add 2, we get 1, the absolute value, when y is going to be equal to 1. When x is minus 1 here, when it's squared, it becomes, pardon me, it becomes positive 1, and then you have to multiply it by this negative half. It becomes negative 1. When we add 2, y is 1. So because they both end up on the same y, it will be continuous. And because this one owns minus 1x and this one doesn't, it will be a function. So we're talking about the absolute value of x plus 2 when x is smaller than 1. So there you can see, there's the vertex, and then it starts to climb. And then it's the same parabola as this, but it's been elevated by 2. And it's for when x is bigger or equal to minus 1. So you can see that the top one, the top one includes -1. So if I follow the red line, I'm going to see a dot for there. But if I follow the blue line at -1, it's going to be undefined, which means it's a function and it's connected. It's continuous. You will see these functions in life actually when you look at ecosystems. So if you look at a rabbit's growth curve and a wolf's growth curve, and the wolf's growth curve will go up the more rabbits there are, and as the wolves eat all the rabbits, the wolf's growth curve will go down as the rabbit's growth curve goes up, and you'll see what's called a combined function. But that's not this, but it gives you an idea that these things can exist in complicated systems. Let's look at this next one. We got a function, a root function as long as x is smaller than 4, and anything bigger than x is equal to 4, we've got a growth function. So what is y when x is equal to 4 here? Y is equal to 2. And this one's including the 4, and what is 2 to the power 4? Y is equal to 8. So they're not going to be continuous at all, but they will be functions. So let's see if that's turned out to be true. So our first function is going to be the square root of x. I think it was, no, was it square root or just square? SQ of x? No, I forget what the square root is. Yeah, there we go. SQRT of x when x is smaller than 4, not including, and when x is 2, when y is equal to 2 to the power of x. And you should, I'm not, I should be doing it in f of x here, to be honest with you. I should be doing all of it, but I tend to use y so that people can see it at first and then include it. Now, when y is bigger or equal to 4. And you can see that there's no continuity there. And it's actually still a function. You can see it's undefined on the red line, but it's defined on the blue line at 4. And it accounts for all values of y. Still a function, still passes the vertical line test, but it's not continuous at all. And what's this next one? We got a reciprocal function as long as x is smaller than 1. And then from that onward, we're going to have a downward facing line. So what is y when x is equal to 1 here? Y is 1. And what is y when x is equal to 1 here? Y is -1. So you can see you're not going to have a continuity here. So we'll do f of x is equal to 1 over x when y is smaller, but not including 1. And f of x is equal to -x when x is bigger or equal to 1. And it's an interesting graph. It's still a function. It's got a vertical asymptote and a horizontal asymptote, and then it continues on here. So it's a function, but it's not continuous. There you can get a good idea of what they want you to learn. They just want you to learn different graphing techniques. Write the algebraic representation of each of these, state the domain of each piecewise function in question 3, and comment on the continuity. Okay. Let's do that. I'm just going to enlarge this first and just isolate this question. And it's just 3 and 4. Okay. Let's look at what these could be in terms of, and I should actually stretch the whole thing down. Let's look at what these could be in terms of functions. Well, clearly on the left it's a parabola. And what's that defining moment? Well, when x is smaller, and does it equal 1? Yeah, it's a solid dot. So equal, smaller or equal to 1. We're talking about a parabola that has a vertex of -2. So it's probably f of x is equal to x squared minus 2. It's just a parabola that's been lowered by 2. And then from onwards we have this line, and we'd have to figure out the slope of this line. Well, we've got 1, 2 here, and 4, 5 here, which means delta y is 3 and delta x is 3. So it's just a simple line, that's been elevated 2 up. So we're talking f of x is equal to x plus 2 when x is bigger than 2. Why just bigger than 2? Because there's a hollow circle here. So let's see if we got it. So we're talking about a normal parabola x squared that's been lowered by 2 when x is smaller and equal to 1. And then we're talking about a normal line that's been raised by 2 when x is not bigger or equal but bigger. So there we have the graphic representation. And if I'm going to put it in proper like notation over here, it's going to be something like this. It's going to be f of x is equal to x squared. And sorry about that, I can't really do. I'll just leave it blank for now. Minus 2, comma, when x is smaller or equal to 1. And it's equal to a normal line elevated by 2 when x is bigger than 1. And don't forget, you've got to have this there. And you actually only have one equal sign once. And then you have a big old bracket to say the function is both of these functions, depending on what x is. So essentially, they depends on the domain. And that's how you would write that piecewise function. Is it continuous? No. There's a big gap there. Is it a function? Yes. Yes on function, no on continuity. And what about this one? This one we have an absolute value that's totally normal, except when it reaches there. And we can't quite see if it's included in both lines. When they have the dot like that, it implies that it's included in both lines, except that they say it's indeed a function. So I'm going to have to assume one of them is included, one of them is not. So that means one of my functions is y is equal to absolute value of x when x is smaller, and I'll just make it included in this one, or equal to 1. What about sideways here? We've got looks like a root function. It could be an exponential on the side, but let's go with the simplest thing. That starts at 1, 1. It has a point here, 4, 2. 4, 2, and 1, 1. So you could say that's probably a normal root function that's been raised by 1. So it would normally be a square root function of x that's been raised by 1, because it starts, and actually it's moved to the right by 1 as well, and possibly raised by 1. Either that, let's see, 1, 1 is the normal, and 4, 2, actually it's just a normal square root function, not raised at all, but just starting at this. So let's try it out. So we've got a absolute value for the first one when x is smaller or equal to 1. And on the next one, we've got our normal SQRT of x when x is bigger. And if I zoom in, sure enough, there's our 1, 1 undefined on our root function. There's our 4, 2. So the reason I realized it was just a normal function is because I can see its basic points haven't changed. They've just eliminated the bottom start. So if I put this to 0, you'll see that it's a normal root function. See? And it's continuous. And it's a function because it's defined on the red line, but it's not defined on the green line. Now, they didn't graph it very well over here, but because they say it's a function, we have to assume there's not a double overlap at that point. State the domain of each. So the domain of both of these is XER. State the range. So y is bigger or equal to minus 2. Y is bigger or equal to minus 2 on this one. And on this one, y is bigger or equal to 0. The comment on the continuity we already did. This is a function that's continuous. This is a function that's not continuous. Hope that's clear on what's going on. They're just two functions slapped together. Graph the following piecewise function. So let's do the same thing we did before. Let's kind of guesswork on what kind of function it is, and then we're going to let Desmos do it. Okay. Here we go. And I'll include number 7. Now, I'm not great at all piecewise functions. So what's this first function when x is smaller than 1? It's minus 1. It's clear that we're just a flat horizontal line. And when x is bigger or equal to minus 1, we're a flat horizontal line that's up at 3. So clearly they're not going to continue. They're not going to connect at all. So this one's just equal to 2 when x is smaller or equal to minus 1. And when this is bigger than minus 1, oh sorry, this one doesn't include the minus 1, and this one does. And it's not a root function, it's there. So there you go. That's like the post office example. So this one does not include the 1, and this one does include the 1, and that's how you know you got it right, or the minus 1 rather. And they are functions, but they are not continuous. And the domain of this one is XER, but the range is equal. Interesting, the range is either y is equal to 2 or y is equal to 1. So you would state that as this. Y is equal to 2 and comma 3. Sorry, not 1, 3. That's because y is always this horizontal line or this horizontal line at 3 or 2. What about this next one? So this is a downward facing line when x is smaller than 0, so it's going to come from the bottom. And this one's just a normal line when x is bigger than 0. Oh, actually, no, this downward facing line goes like that and like that. So it's actually, this is actually the definition of an absolute function. So let's have a look at that. So it's minus x when x is smaller or equal to 0. 0, not 9. And when x is bigger, not equal to 0, we're just a normal function. And look at that. We get pretty much the definition of an absolute function. The only thing they didn't really, 0, 0, in this case belongs to the red line and does not belong to the green line, which doesn't happen. And you're going to learn some interesting things about absolute function. But they've essentially graphically represented an absolute value graph using two separate lines, one with a -1 slope and one with a +1 slope, and they've made them connect at 0, 0, so it's continuous. Okay, what about this one? We have a parabola that only exists when x is smaller than 2, and it's elevated by 1. So that means when x is 2, 2 squared is 4, y is going to be 5. Then we have a flat, a two-slope line that's 1 raised, and when x is 2, we get 4 plus 1, 5, y is 5. So it's quite clear they're going to be continuous because this one includes the 2 and this one doesn't, so they're going to be functions as well. And that's how you see if they're continuous, is where does one end and where does the other one start when you plug the x value into the formula that you're given. And sure enough, there it is there. We have a parabola whenever x is smaller than 2, and it's undefined because it doesn't include 2. And then we have a line that includes 2, and they are connected because where one ends at y is equal to 5, the other begins. What about this next one? This next one's a line that's elevated by 2, and it's interesting, it's only when x is between and equaling -1 and 3, and then only bigger than 3, it's going to be a flat line at 5. So let's figure out what this first one, when x is 3, what is it going to be? It's 3 plus 5. So it's going to be continuous, except way here on the left, we're not going to have anything continuing. Now, I think technically this is a continuous function for the function we're dealing with, just the way a root function is continuous. It's a good question, actually. But let's draw it and make sure. So when x, we're dealing with a line when x is between and equal to -1. Excuse me. 3, and then we're just dealing with a horizontal line of 5 when x is bigger than 3. So they are indeed continuous for what's given. And you can see 3 includes the dot 3 comma 5, and the green line does not include the dot 3 comma 5. And we zoom out, they're continuous. What's their domain? Well, x is going to be from -1 to infinity. So you do it like this, -1, smaller or equal to x, smaller or equal to in positive infinity. And in functions notation, I think that's written as a curvy bracket -1, comma, positive infinity on the right side with a round bracket, because you never include infinity in your thing. So I guess I should actually have smaller than infinity here. because you can see from the graph there's no x values below. And what's the range? Well, it goes anywhere from 1, positive 1 here, up to 5. So the range is 1 is smaller equal to y is smaller equal to 5, which would be written in notation as, it would be written in notation, function notation, as curly bracket 1 comma 5 curly bracket, which means it goes from 1 to 5, including 1 and 5. I'm going to have to verify if that's the curly bracket you use in function notation. Then they go to a practical example, number 6. So I'll enlarge it. They say Graham's long-distance telephone plan includes the first 500 minutes per month in his charge. So how's that written? It's just saying for your first 500 minutes, you've paid $15. You get 500 minutes free. For each minute after 500, so that means bigger than, he's charged 2 cents. Write a function that describes Graham's total distance charges in the number of distance minutes he uses. So you just start with y, or if you want f of x, or if you want cost based on minutes, C of m, is when it's below, when x is between 0 and bigger is smaller or equal to x is smaller or equal to 500 minutes. His cost is a flat rate, $15. Okay. When x is bigger, not including, because you got to decide whether the 500 minutes goes with this charge or this charge, and since they say for each minute after 500, I'm going to say it's bigger than 500, he is charged 2 cents on top of that. Now be careful, don't write that as it's just 2 cents, because that implies after 500 minutes you don't pay the $15 anymore. You pay just 2 cents. But in truth, it's the $15 plus 2 cents per minute, so 0.2x. In other words, you're getting charged $15 plus 2 cents for each minute. Let's see if we get that right. So we're going to pull up this, and we're going to say, okay, you get charged 15. Let's do it in f of x. I don't think, well, he might do cost of m, might do c of m, is equal to 15. As long as 0 is smaller or equal to x is smaller or equal to 500. Okay. After that, yeah, I can't handle, oh, sorry. It wouldn't be x, it would be m. Yeah, I can handle it. And then after that, my c of m is going to be the original $15 plus 0.2 cents, that's 20 cents, 0.2, that's 2 cents, times the minute, for every minute bigger than 500. Let's see if they're connected. So it helps if I just change my y-axis to show like 0 to 1,000 and do steps of 100. And then my x, sorry, I should have done my x-axis that. 0 to 1,000 in steps of 100. And then my y-axis, I just do, 15 to 17 or something. And put it like that. And then just click home. Okay, so we can see, I didn't quite do the steps properly. We can see everything's $15 until we hit 500. And then it's going to be 15. Oh, for each minute after. Oh, that's interesting. So it's going to be, let's make sure the question. He is charged, for each minute after 5 minutes, charged 2 cents. So that's actually not going to be minutes, 500 minutes, because suddenly he's paying a huge amount. It's going to be minutes minus 500, because it's going to connect. So that means if you're paying $15, or 500 minutes, you're paying 15. But as soon as you're after that, you're going to pay a little bit more. You see the y value is going up? It's going up 2 cents. So if you want to see a charge, you can do like C501, and that should be 2 cents on top of the 15. Oh, it doesn't know which one to do. So let's go back and just use that as f of n. So sure enough, if I do C501, it's going to recognize this function and tell me I'm paying $15 plus 2 cents for that extra minute. Why did I do m minus 500 here? Because the first 500 minutes here are included in the 15, and you're only charged 2 cents for each minute after 500. So you have to do m minus 500 because we've hit 500 and more, and you've got to do like one for each minute. For instance, 501, it would be 501 minus the 500. It would be 1 minute times the 2 cents, and then add the 15 charge. This way you can see any cost. Let's say he goes 600 minutes that month. He's going to pay $17, which makes sense because it's $15 for the first 500, and that extra 100 minutes times 2 cents is $2. So it's $15 plus $2, $17. And graphically you can find it as well. So you can always, and that's where I wish this had done better. 0 to 1,000 and step there. That's a bit better. And my y, I just want it to go from 15 to 17 in steps of 1. Okay. There. That's a better visual. And you can see, okay, it's 15 bucks, 15 bucks, 15 bucks. Oh, it's going to cost me more as I go up. Now, what happened there? It shouldn't be this steep. Oh yeah, it just looks steep. So if I hit 17 here, it should give me 600. Yeah, close. Come on. There we go, 600, comma $17. So 600 minutes, 17. And there you get a graphical, and it's much more obvious now. You can find out anywhere on this chart, the left number will be your minutes, and the right number will be your cost. Anything below 500 minutes is going to cost you $15. And of course, nothing exists over here because there's no negative time on your phone. All right, now the question is, see here at 0, we would include $15 because whether you use your phone or not, they're going to charge you $15. And it's continuous. It's not defined on the blue line, but it's defined on the red line, and it's a function. The reason you'd have to include the 500 on one or the other is because when you hit 500 minutes, the phone company is going to charge you something. Which graph is it going to use? And there you go. Just you had to use a bit of logic there. Many income tax systems are calculating using a tiered method. Yeah, under a certain tax law, the first 100,000 is subject to 35%. Anything greater than that, up to 500,000, is subject to 45%, and earnings greater than that are 20%. Write a piecewise function. Okay, so how much taxes do I earn between 0 is x and up to 100,000? It's pretty clear from the thing that my taxes are going to be, let's call my taxes are going to be equal to, what percent did they give us? 35%. What's 35% in decimal? 0.35 times my x. So whatever my x is, I'm going to be charged 0.35 in taxes. What is my y going to be charged? Now here's the tricky part. Sorry, what is my taxes going to be when x goes from 100,000, but not including it, up to and including 500,000? Well, my taxes are going to be 45%, 0.45, but not times x. It's going to be x minus that amount that we started at, because you're only going to be taxed on that amount. But don't forget, we're also going to be taxed 0.35% on the first 100,000, because you've hit your max here, so you're going to be charged that, and then we're subtracting 100,000 from this x to figure out how much you're charged to tax up to the next 500,000. And the reason you do that is because otherwise you get double taxed. If I just did 0.45% times x, it's going to calculate the 0 to 100,000 that we already paid 35% on, and that's not how tax works. They're making you pay 45% on the tax from 100,000 to 500, and then you have to pay the full 35% on that first 100,000. Because obviously, if we're in this tax bracket, we've already exceeded 100,000. The next tax bracket, which is 500,000 and up, so when X is bigger than 500,000, we can't say bigger and equal because we included the 500,000 in the background, taxes are going to be equal to 0.55, that's 55%, of my X minus 500,000 plus 0.45 of 400,000. Why 400,000? Because from 100,000 to 500,000 is 400,000, and we've definitely hit that bracket if we're above, plus 0.35 times the original 100,000. And that should produce a continuous graph that connects all our tax brackets, and it should be a way of determining it. Now, how would I do that in function notation? Instead of taxes is equal, and X, I'd say tax based on income is equal, and then I would have all those conditions, 0.35 times income, and the same thing I just wrote, but with income. Income, and you'd also put in the ranges. It's the same thing. If you want me to do it, you'd say like this: when 0 is smaller or equal to income, smaller or equal to 100,000. We're just going to need a bit more room. And you'd say it's 0.3545 income minus 100,000 plus 0.35 times the 100,000. That's the first 100,000 you've earned. And then the last one is 0.55 times income minus the 500,000 plus 0.45 times your 400,000 that you've definitely already earned. And sorry, I don't have enough room here. Plus the 0.35 of the first 100,000 you earned. That's because we know you've exceeded 100,000. We know you've exceeded the next 400,000. So we know you're paying 0.45 max on that and 0.35 max on that. And then whatever you make extra, you're getting charged 0.55. And again, you would put these limits over here on it. So you would put when X is bigger than that, this is true. Well, you know what I mean. This would be for that one. This domain limitation is for that one. And this domain limitation is for the last one. You put it after, and then you do TI is equal to a big bracket, and you'd list each of these formulas with the domain limitations right there to say this will take care of any tax calculation you have. Let's see if that's true. So we're going to pull up Desmos, and we're going to just get rid of this piecewise, and we're going to say my taxes based on my income is equal to 0.35 times my income, as long as my income is between 0 and smaller or equal X, smaller or equal to 100,000. Boom. Let's see if it recognized it. So it's got an issue. Probably got to be a small t. Probably got to be a small I. Oh, I know what I did wrong. As long as I. There we go. Boom. Now, how come visually that's terrible? Because it can't. It always does one each here. So for our graph, we're going to go from 0. What was our maximum income? Let's say 750,000. And we're going to go in steps of 10,000. Okay. And for our Y, how much taxes we pay, that's going to be harder to show. We're going to need, what's 0.55 of, so we're going to need at least 400,000 in steps of 100,000 as well. So hopefully that works. Yeah, there we go. So we have a nice graph, and this shows us the left is how much income I'm making, and the right shows how much taxes I'm paying. I'm going to be paying 35% of whatever I make. And you can even calculate how much your net profit is by subtracting Y from X. So for instance here, you're going to be making roughly $41,000 in your bank, and the rest goes to your IRS or Revenue Canada. Okay, let's do the next tax statement. Let's call it T2 though, of I is going to be equal to 0.45 times I minus the 100,000 plus 0.35 times the 100,000. And that should connect us. And then don't forget your limitations. That's when 100,000 is smaller than X is smaller or equal to 500,000. Now, I shouldn't have made X. I should have said I, and boom. We should have connected there, and then here it'll say undefined. Yeah, but it's connected. So suddenly it's adding the two together, and as I make more, I'm getting taxed more. Okay, all the way up to, what was the limit? It was supposed to be 500,000, so I didn't quite do the limit. No, I did it. Yep, right up to 500,000, which is there. So there, yeah, it ends and includes there. And then finally, the last income calculation or tax calculation, which I'll call tax 3, is based on your income, is going to be 0.55 times I minus the 500,000 that you already made, plus 0.45, not times 500,000, but 400,000, because that's how much you made on top of that first 100,000, and then 0.35 times 100,000. Now all this takes time, and then you've got to put in your range limitations when X is bigger than 500,000. Okay. Now it should have been connected, so let's see what I did wrong. So you get tax 0.55 when the income is bigger than 500,000, plus 0.45 times the original 400,000, plus 0.35 times the original 100,000 when X is bigger than 500,000. So that should have appeared. And so I've done a minor calculation error somewhere because I don't see it. Oh, I know what I did. It's X. It's got to be I. And there, sure enough. Now that one, see, there's three distinct graphs, and you can't quite see the slope as well. So I'm going to try to stretch out my X. Oh, no, I wanted to stretch out my X, not my Y. Yeah, it didn't quite do it for me. So let's see if I can do steps of 5,000. Let's just do 0 to 100,000. See if it steps of 1,000. See if it does it that way. Now, anyway, you don't get a good idea of the slope, but you can calculate your taxes exactly by clicking on it, and also by subtracting. You can calculate your net taxes, and you can see when you hit this tax bracket, you're paying a hell of a lot of taxes, and that's why a lot of people go and look for ways to reduce their tax. In Great Britain, at one time, taxes were 70%. Helps know your history. So there's that. Let's go to the next one. Sorry for the confusion. If you want clarification, just put it in the comments or get in touch with me, and I will try to help with a specific question. Okay, so these are all like scenarios. Can you think about them? Now, just keep in mind that k is a missing number. Find the value of k that makes the following functions continuous. Well, that's quite simple. This just has to end where this starts. Well, we know there's no k in this one, so we can figure out where this one starts since they both end at minus 1x. So when minus 1 is x here, I get minus 2, and minus 1, I get a minus 3. That means I have to end at this one at minus 3. Since I have a partial formula for y, it's x squared minus k, I know that's going to equal a y of where I want to end, minus 3. I'm trying to solve for k. You might say, well, we don't know x either. Sure we do. It's where it ends, minus 1. So what's minus 1 squared? It's 1 minus k is equal to minus 3. Let's take this 1 to the other side. I get minus k is equal to minus 4. Divide both sides by minus 1. and I get k is equal to 4. Therefore, for this to be true, for this to be continuous, k must be 4. Let's test that out. Let's say that's x squared minus 4. So we're just dealing with a parabola that's lowered by 4. When x is minus 1, we get 1 minus 4, and it ends at minus 3. When x is minus 1 here, we get minus 2, minus 1, minus 3. So sure enough, when k is 4, these two graphs will be continuous, and you can always use Desmos to make sure. I hate to get rid of that income tax graph, but so you get y is equal to x squared minus 4, and I think when x, whatever, we'll just say when x is smaller or equal to minus 1, and we'll say y is equal to x, was it x plus 1? Let's see. It was 2x minus 1, and x squared minus 4. 2x minus 1. And then when x is bigger than 1, minus 1. And that didn't quite work out. So let's see what I did wrong. X squared minus 4. And that's at minus 1. 2x. Oh, hang on. There we go. It's just that it's being drawn crazy. So there we go. It ends there, minus 3, and then continues on the line. And it's continuous, and I've included it in the blue line, but not in the green line. Thus, it's undefined on the green line, defined on the blue line, which means it's a function and it's continuous. Those things are easy to understand if you understand the basic concepts of time-wise functions, piecewise functions rather. The fish population, 1,000 is a lake. So here it's normal growth, and then suddenly it becomes a flat line. So one, it's going to be a normal growth curve, and then suddenly it's a flat line, which means something happened there to hurt the fish population. Either people are fishing, and people are fishing perfectly to keep the population constantly growing, or there was a pollution event, or a dam, or an invasive species, or a lack of food, or whatever. There it says, due to a chemical spill. Sketch the graph, okay? So where does this one end? Well, at 0, it's at 1. So y is 1. And when it's 6, 2 to the power of 6 is, get used to your calculator too, 64. So it goes all the way to 64. The question is, does this start at 64? Probably not. So at 6, we get 4 times 6, 24, plus 8. It's 24 plus 8, 32. So it doesn't look like this. It's a normal growth function until it hits 64,000 fish. Probably it's probably based on thousands of fish, not just 6 fish. So 64,000 fish. And then suddenly there's a chemical dump, and the fish start down here at a population of 32,000. But they're consistently growing. And at some point over here, it's going to reach 64,000 again. So it's eventually going to rebuild. And they're probably going to ask you when this line equals 64,000. And for that, you just make it 4x plus 2, plus 8 rather, equals 64, which is this line equaling 64. And the reason I'm doing 64 is because I'm the one who added 1,000. Yeah, there we go. See, in thousands. Sketch the graph. Okay, I've done it roughly, but I'll do it better. Describe the continuity of the function. It's discontinuous. The fish suddenly died off. How many fish were killed? Well, it was 64,000 here, 32,000 here, so 32,000 fish died. And it's really just 64 and 32, but the graph is in thousands of fish right there. At what time did the population recover? So when will this equal 64? Okay, well 4x is equal to 56, and that's just putting 8 on this side. And then divide both sides by 4, and I get 25 and 3, 28, and I get 14. So when the time reaches 14 years, the fish population will be 64,000 again. And you can see that from the graph. Describe other events relating to fish population in the lake that might result in piecewise functions. Sure, that's easy. And this is where your biology comes into play. Acid rain, predators. So sometimes people accidentally introduce something like a predatory fish, usually from a pet store. Happens a lot in Florida. It also food. So let's say the weeds die from probably the other causes, right? Or competition for food. There's another fish eating the food. But when a huge drop like that, this one's probably not as likely. But definitely this could be. And then what else can affect it? Fishing, right? Drainage to the lake. Anything drastic that would happen to the lake. Pollution, as described. So all these things can affect population. And then as you learn in ecosystems, there are so many factors. That's why ecosystems are hard to study. But you have to do piecewise functions like this and combined functions to study them. And if we were to graph this, so it's just 2 to the x. When x is smaller than 6, x is smaller or equal, say smaller or equal to 6. And then from onwards, it's 4x plus 8 when x is bigger than 6. And that's not 2 squared, it should be 2 to the x. There we go. So sure enough, there the population reached 64. Then something happened. And suddenly it reaches a population of 32. Or 30. Actually, I did a calculation here. I might have just written the formula down wrong, though. Hang on. Yeah, it's 4x plus 8, not plus x, plus 8. So sure enough, at 32. And if you want to put an equal sign in here just to see it. Right, it'll be on this side, equals. So that you can see it, there's 6 comma 32. And I'll just get rid of it now. And then you can see, just by making a line of y is equal to 64, you can see what year it happened when it came back to 64 in the green line. And sure enough, the x value is 14, which means if I change this to an f of x, and I do an f of 14, I will get 64. And these tools, Desmos especially, is fantastic for graphing and understanding the graphs. I strongly urge you to both be able to draw it, but use Desmos to verify your logical conclusions. All right. Create a flowchart that describes how to plot a piecewise function with 2 pieces. Now, leave that to your teacher. An absolute value function can be written as a piecewise function, as we saw, minus x and positive x. Write the function of f as a piecewise function. Okay, so this is just a absolute value that starts 3 to the left. So if we were to just use this absolute value of 3 to the left, so x plus 3, that's going to help us really understand how to graph it. So we're going to talk about a negative line that essentially starts 3 to the left. So we do y is equal to negative x, and it's going to start 3 to the left. And then where it's only going to be for values where x is smaller or equal to minus 3. There, I got the red side of it. Now I'm going to do another line where y is equal to x minus 3, but only for x values bigger than minus 3. And why didn't that work? Oh, because that lowered it by 3. My bad. To make it go to the left by 3, I would have to put it in brackets? No. How do I make, I don't know why I had a brain fart here, but it's going to be y is equal to x, and to get it to the left by 3, I believe I still just have to do x plus 3. Oh, plus 3. I'm an idiot. Sorry, it's not minus 3. Because it's the opposite for x. And then I have to make my limitations equal to that. And sure enough, if I turn off this top one, oh, sorry, it's got to be bigger than minus 3. If I turn off this top one, and even if I turn off the blue, and then the red, you can see I did 2 line functions, shifted them to, you might say, why is that shifted that way? Well, here, look, if I do it properly in notation, proper notation, with the brackets, you'll see it still works out. So there's the red line. It's shifted to the left, and this negative makes it a downward line. And this blue line is just a normal line shifted to the left by 3. And when I connect them, I get the same thing as this absolute value graph up above. The demand for new CD is described as this. So you got 1 over p squared. So it helps if you understand that parent graph. That's what that one looks like. It's a pretty funky graph. It's like a positive version of a rational function. And then the rest of the question says, so the demand for the CD when it's between 0 and 15, so we're only going to be working with the right side of the graph, is that. And it's 0 as soon as the demand goes up to 15. Okay, let's just let it graph it for us. So from 0, let's say x is smaller or equal to 15, and then when y is equal to 0 for x is bigger or equal or bigger than 15. And even on this one, let's put the 0 in there to get rid of them. There we go. So all the way, and then suddenly at 15, we have almost 0, and then it jumps down to 0. Now, I hate to tell you, but it's not going to be continuous, because when we plug in, if I change this to f of x, and I plug in f of 15, it's going to be above 0. It's going to be slightly above 0, but it's still going to be above 0. And then when I do f of 15, like 0.1 for the other one, so if I do g of x for the other one, the reason I can't name them both the same is because it won't know which one to calculate. And I do 15, it's not going to include it, but we know it's going to be 0, right? 15.1 then, it's going to be 0. So we know that there's a jump of 0.044. There's no continuity. You can see it when you zoom in. You can't see it when you zoom out. So it's pretty much, there's a demand for your CD that goes down dramatically for some reason as you sell more of them. Well, I guess that makes sense. The more people have it, the less demand there is until nobody's buying it. Yeah, so it's discontinuous. It's pretty obvious why, because that's going to yield a result and that's not. Extend and consider this function, takes an element of its domain and rounds it down, and there's 10th. No, I'm not doing this. Explain why there's no value of k that will make the following continuous. Okay, I think we can do this one. The first thing to do is figure out the function that has all the information we need. Okay, so which one of these doesn't have a k in it? Well, obviously the last one. Okay, and that's when x is bigger than 3. And this is when x is between this range, and this is when x is smaller than this range. So let's figure out what this is when x is 3. Well, 3 squared is 9 times 2 is 18. So when x is 3, y is 18. Let's look at here if we can achieve an 18 by coming up with a k value, because for it to be continuous, this line has to lead into that line. Well, we're going to look at 3 again, and we're going to ask ourselves, x plus k, can it ever equal 3 when x is 3? Yeah, 3 plus 0 is going to be equal to 3. So in this case, k is equal to 0. So if k is equal to 0, we can just take it out. And then finally, the last question is, when x is minus 1 here, what is the y? Well, when x is minus 1, y is minus 1. So we just have to see if this can end at, if this will yield minus 1 when x is minus 1 here. And it doesn't. When x is minus 1 here, y is minus, sorry, let me write it down. When x is minus 1 here, y is minus 5. So this is the problem right here. This one's going to go along like a line, and then there's going to be a big gap. It's going to be minus 1, down to here. Up to here, actually. Then it's going to just be a normal line. And then suddenly we're going to have a connection here and make a parabola. But there's going to be a big gap between here. And there's no value of k that can join this, because this must end. This must start where this one ends, and this one must start where this one ends. There's no possible value of k that'll work, that'll get 18 and still get to that. And so that's really all you have to focus on, is on the one you know for sure, and see if that one can be made to end there. And you can reverse it too. You can see if there's a value of k that will start here, and then see if it ends up at 18. You'll discover it doesn't. So looking at reverse, this one ends at minus 5. So can this x plus k ever equal minus 5 when x is minus 1? So minus 1 plus k. And how did I get the minus 1? Well, because it's starting where this one ends. Minus 1 plus k equal to minus 5. Yeah. When k is equal to minus 4. So now we have x minus 4 as the second equation if we're going to connect it to this one. The question is, at 3, is it going to be equal to 18 where this one starts? So obviously when x is 3, x minus 4 is minus 1. So it does not connect with the 18. That definitely starts this one. So no matter what value of k I put in there, I can't connect either the first or the last function. Hope that one was clear. That's just kind of logic. No. Create your own piecewise function using 3 trans. Okay, well, you can just do it yourself. You just have to make sure where one ends, the other starts. The easiest thing to work with always are lines. So you can just say, okay, I got a line on the left side that's minus x plus 4, and it stops at x is equal to 2. So just say x is smaller than 2. You say it goes all the way to there, and then you got to obviously figure out where that one ends. You can say my equals if you want to figure out where it ends. Or you can just calculate it. It ends at 2. So your next line can be y is equal to x plus 2. X. It's being shifted. It ends at 2 comma 2. So it's going to be shifted to the right. So x minus 2, and then it's going to be shifted up 2. And then that's for, you can put whatever range you want. 2 is smaller than x is smaller than, let's say, 4. And then you can do another line that's got to start where this one ends, which is, if we want to figure it out, smaller or equal to 4, it ends at 4. So now we can do starts at 4 comma 4, so now we can do another negative line that is shifted right to the 4 and up 4. Sorry, shifted right 4 and up 4, and then only for values beyond 4. So x is bigger than 4. And boom, we've connected 3 lines successfully that are a piecewise function. You just have to figure out where one ends and where you can start the next one, and then when that one ends and where you can start the next one. You have to make sure that one of the values is included in the other one and not included in the next one. There you go. I'm not going to do theoretical ones. Talk to your teacher about that one. So next we'll do exploring operations with functions. Sorry if it's long. This section's not as important as most.